Welcome to a short discussion about the basics in gearboxes. So a gearbox is normally placed just immediate to a prime mover in order to get various output speeds so as to apply to the applications. So according to the number of speeds that is needed in an application, a gearbox can be designed. What you're seeing are the gearbox fitted to the basic engines. So now, a gearbox is basically defined by its structural formula. So before going for the design, we have to fix the structural formula of this gearbox. So the structural formula consists of small n, which is the total number of speeds to be needed in the gearbox, and P represents the speeds in each stage, and X represents the spacing in each stage. Say for example, P1, number of speeds in the first stage, and x1 is always kept as 1, and x2 is equal to p1, and x3 is equal to p1 into p2, and if we have x4, it goes as p1, p2, p3, multiplication of the speeds in various stages. So here the structural formula can be read as n equal to p1 of x1 into p2 of x2 into p3 of x3. So here you are going for the next part of the design. Say for example, if we are about to design a 12-speed gearbox, this 12 small n, the total number of speeds that is desired, has to be split into the multiples of 2's and 3's. So normally we used to split into the multiples of 2's and 3's. Say for example, we can write this 12 as 12 is a multiple of 3 into 2 into 2. So here we have 3 different speeds at each stage. Say for example, 3 is a stage, next 2 is a stage, and the other next 2 is a stage. So therefore, we have here totally 3 stages of speeds in this gearbox. Say for example, these stages and speeds or the speed distributions are explained through a ray diagram. So what you are seeing is an example of a 12-speed gearbox ray diagram. So this ray diagram, to start with, the ray diagrams are having horizontal and vertical lines. This horizontal lines denotes the total number of speeds that are obtained in the gearbox, and the vertical lines denote the shafts which are being used in the gearbox. Say for example, if we are designing a 12-speed gearbox, automatically we will be having 12 number of horizontal lines. They are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So, next slide please. And the next drawing what you are seeing is the kinematic arrangement layout. Kinematic arrangement layout. So here, it is something like a top view of an open gearbox. When you just open a gearbox and see from the top, it is something like this. So here you have 1, 2, 3, 4 shafts, which represents the shafts or with respect to the centers with which the gears are rotating. And here, these separate gears are called as fixed gears, and this complete set, this one are called as sliding gear sled. So normally, to define a gearbox, we use ray diagrams and kinematic arrangement diagrams for their build-up and for their design. Next slide please. So now we are coming for a complete setup of 12-speed gearbox. So as we discussed before, starting from the structural formula, n is the total number of speeds that we have, or required total number of speeds, and we are splitting this 12 as 3 into 2 into 2. So normally we know that x1 is 1, spacing in the first stage, and the spacing in the second stage is nothing but p1, which is equal to 3, and the spacing in the third stage is p1 into p2, which is nothing but 3 into 2 equal to 6. So the structural formula gets arranged like this: 12 equal to 3 of 1 into 2 of 3 into 2 of 6. So this is the total structural formula of a gearbox. So now, going for the ray diagram. Actually we have a Shaw formula, and the step goes like this: 5 power n minus 1 equal to n max by n minimum, where n max is the total number of maximum RPM and n minimum is a minimum RPM of this gearbox. So by having these two, maximum and minimum RPMs in the gearbox, we can find the step ratio. So going for a standard step ratio, you can select the speeds that are available in various series as R20, R5, R10, R40 series, which are the most standardly used series for selecting the preferred numbers. So from the preferred numbers, we obtain the 12 different speeds according to the range of the maximum and minimum RPM. So now, starting a ray diagram, first we have to draw 12 horizontal lines equidistantly and mark the speeds from the bottom as in the diagram, and the vertical lines denote the shafts. So as we saw, 1, 2, 3, 4 shafts are there, therefore we have 1, 2, 3, 4 vertical lines, and we have to start from the third stage. Say for example, this is your first stage, this is your second stage, this is your third stage, and this is your shaft 1 or input shaft, this is shaft 2 which is an intermediate shaft, and this is a shaft 3 which is also an intermediate shaft, and this is the output shaft, shaft 4 or output shaft. You can name accordingly. So now, the distribution of gears, as we saw, P1 is 3, so we have 3 fixed gears, and P2 is 2, so we have 2 fixed gears, and P3 is also 2, so we have 2 fixed gears. So this is your first stage, this is the second stage, and this is the third stage. So the output of first stage is given as the input for the second stage. The output of second stage is given as the input for the third stage. So now, we have to start our ray diagram from the bottommost speed line, right? So here, how many speeds are in the third stage? This is of course our third stage. And how many speeds are there in the third stage? So you have 2 speeds. So you have to mark 2 speeds totally in the third stage to start your ray diagram. So starting from 160, one speed is marked as 160, and the next, say for example I am marking this one as 160, and the next is with a spacing of 6. So 1, 2, 3, 4, 5, 6. So I am marking the 6th speed. In between, considering this one as maximum and this one as minimum, we have to find one input speed between these two maximum and minimum speeds. We have a relation for that, stating n max by n input should be less than or equal to 2, and n minimum by n input should be greater than or equal to 1 by 4. These two conditions are to be considered, and one input RPM is to be found satisfying the condition. Say for example, when we calculate this 400 satisfies the conditions. So I am marking this one as the input for these two speeds. So now connect a ray for this input and the output. So from one speed as input we are getting 2 output speeds. So these 2 are the 2 speeds that we are getting at the third stage. So now, how many speeds are there in the second stage? It is 2. As we know, P2, it is 2. And what is the corresponding space for this spacing in stage 2? It is 3. We know that x2, it is 3. So after this, 1, 2 and 3. I will mark this one as the 2 speeds that are obtained through one input. Similarly, using these 2 relations, and this one is the maximum RPM and this one is the minimum RPM, you have to find one input speed which is satisfying both the conditions. So when we go for the calculations, we find 630. That means what I am marking here as the best input satisfying the conditions, and I will join the rays as we did in the previous case, and I am joining the rays here. So now coming for the first stage, how many speeds are there in the first stage? P1, it is 3. And what's the corresponding spacing in that? It is x1. Therefore, spacing is 1 and the number of speeds are 3. The first speed is marked here as this one. It is 630 and the next two speeds are at a spacing of 1. So, here the next, and this is my third. So now I have marked the 3 outputs obtained in the first stage. Now, based on the inputs, say for example a prime mover will be decided and its RPM might be known, and when it is known you can go for that particular RPM as the input. Say for example, if I consider a 1500 RPM input motor or an engine, I will mark this one as my basic input and I will just connect the rays as you see. So after this you have to completely close the ray diagram. Say for example, you have drawn this with equidistant, right? So what you can do means you can use a scale and you can draw parallel lines to the speed from the next point and from the next point. So when you draw like that, automatically you will be getting the rays like this. So now second stage is completely over and you have to go for the third stage. So from each input of the speed, how many speeds do we have? We have normally 2 output speeds from each and every input speed. So just again draw parallel lines from each and every point and get the speeds connected. So I am drawing the rays. And the second speed from each input. So now all the speeds must be connected through some ray. No speed must be left blank, or no speed, no output must get 2 rays in connection together. So if that is satisfied, then your ray diagram is completely correct. Now coming for your kinematic arrangement diagram, normally when you have 3 speeds in a stage, you have to put the smallest gear at the center and you can arrange any of the 2s on the sides, other 2 gears on the sides. When you have only 2 speeds, you can put either the smallest one here and the largest one here or vice versa.